Well, thank you very much for the invitation to present what we are doing in MinDat in developing this pretty cool model for assessing vulnerability of slopes along the trunk highway system in Minnesota. But before I start, I would like to acknowledge the major work done by the whole team. The two Nicks and Jen from WSB, who is the consultant who is developing the GIS model. The top members, the advisory panel, who has done a tremendous work reviewing and participating in development of this model. Nathan, Jim, Kristen, Katie, the project coordinator, Shannon, Sarah, Blake, and Amy, all from MinDat. And then Andrew from Terracon and Tony from the University of Minnesota. So we all know that climate change has has increased the frequency of major rain events and therefore floods along not just the Minnesota, but along all states and on the world. Therefore, having tools to quickly assess slope vulnerability, it could be very useful for transportation agencies and for other agencies. So as an example, what happened in Minnesota in 2012, we have a major event close to Duluth, where we have between June 19 and 20, we have major rain that created about 30 or 40 landslides along the state. You can see here a satellite image where we have this rain and flooding turn the southwest corner of Lake Superior muddy brown. So all these major landslides cost more than $50 million in damage for the trunk highway system in Minnesota. So this is happening quite often now. So in this case, we have about 26 road closures on the trunk highway system. We have to do a major effort between the agency, MinDat, and other agencies, the DNR, the Department of Natural Resources, the Department of Public Safety, Federal Highway consultants and contractors to bring this up to speed, to bring the network of roads up to working, because we have some critical infrastructure in these locations that provided power to some local communities, some cities and towns. So we have major events. So that's one of the reasons, the motivations to develop this kind of cool model, which is non-traditional in a way. So before I explain what this model is all about, let me explain what is the traditional approach in terms of geotechnical linear. What do you do to assess slope failure? So generally speaking, you follow these 7 steps. First, you go to the site where you do site characterization. You do in situ and lab testing. Then sometimes you install instrumentation to monitor your slope. Then based on that information, you estimate the lithology, the soil strength, and the pore water pressure distribution in your slope. And then you develop a digital twin site of the slope to compute the factor of safety. For some of you, I understand that we have a lot of students attending. Factor of safety is the ratio between the resisting forces divided by the acting forces. So we want to have, as an engineer, design slopes that have factor of safety larger than 1, because 1 means imminent failure. Then what we do is we provide repair or improvement options. So we either install drains, we cut or fill, we put structural elements to reinforce the slope. And then we compute again the factor of safety. And then we do that cycle until we feel satisfied from the point of view of stability. So that's the traditional local approach, which could be time consuming and very expensive. Then you can do, the next step is, in order to do risk assessment, is you can use powerful numerical tools that we have available. And then assuming or measuring the variability of the soil properties, of your lithology, of the site conditions, water table conditions. If you account for the variability of the parameters, then you can run thousands and thousands of simulations to estimate factor of safety, where you can come up with a probability of failure. With a probability of failure, you can go and estimate your risk based on what we call consequences that I'm going to mention later on. So that's the traditional approach, time consuming, still applicable. But when you are working on a high level approach, network level, what I'm talking about, when you are talking about decision making, you need something that is probably faster and not that time consuming and more cost effective. So that's the goal behind developing this vulnerability model. So we want to have a model where we can have for engineers to assist to proactively. So that's the key word, to be proactive in identifying and mitigate the risk of failure. So not being reactive, not just go and fix after it happens, but trying to be a little bit proactive in it. And it can help us during the project scoping. So when we're developing a new project, we can assess what are the risks of slope failures beforehand and plan ahead. And this model is also attempted to be used for asset managers in decision making and budget allocation. So that's the goal of this model. So this is a GIS model that uses basically two concepts. One is geomorphology of the site, basically the shape of the land, as one of the key parameters for providing this rating of vulnerability. And then uses what we call the geographic weighted regression. So it's pretty much similar to linear regression, where you account for local variation of the parameters that are key. And to minimize bias and subjectivity. So that's kind of the two components of the model. How do we compute the vulnerability score or probability? So we compute probability based on this logistic equation. And what is cool about this is that these parameters, these linear regression parameters, vary according to the region of the state, because the state has different geology. It's very complex, so these parameters will change geographically. And the independent parameters are what we consider to be the vulnerability factors that I'm gonna mention later. So how the model is developed. So these are the 5 steps that we use that we follow for the development of the model. First, we select some preliminary vulnerability factors and interaction terms between them, based on, like I said, the shape of the land, hydrology, and in general, the geology of the region. Then we go and check the vulnerability rating using these preliminary inputs. And we check that with historical slope failures that we have on record and in databases. Then we do a sensitivity analysis to determine which are the parameters that drive the rating of the vulnerability. And then we move to step 3, which is the selection of the final parameters based on this rigorous statistical analysis. Then we go back into the field to verify if that final model still is able to predict both failures and stable zones, because we don't want to have a biased model that is just too heavily developed based on failure cases. We want to have also cases that did not fail. If this is required, we do further adjustments on those weighting parameters that I showed you early on. So the model, actually this effort started 3 years ago in 2017. So it has been a massive effort. And because the geology of the state of Minnesota, it changes according to different locations. So we divided the development of the model in 3 phases based on the geology, as you can see here. We have, like, for example, phase 1 includes steep terrain with bedrock exposures. So we have that location here where we have the Twin Cities, the metropolitan area. But then, for example, phase 3, which is the yellow here, we have is a region with low relief, very gradual slopes, and we have like glacial deposits of Lake Agassiz clay. So there we have quite different geology. Then in the Duluth area, we have bedrock outcrops. So we have rock faults type of failures. So very different geologies, and that's why we split the project in 4 phases. The final parameters that we selected, the vulnerability parameters for each phase, are listed here. As you will expect, one of the key ones is the slope angle. It's kind of obvious. Then we have, for most of them, we have the terrain curvature. So that's where the geomorphology comes to play. So either if you have a landform that has a concave or a concave shape or convex, it will change the vulnerability rating. And then we have other parameters like local relief, like incision potential. In some locations, water table is important, like phase 3, where we have those gradual slopes, like shallow slopes with clay. Water table is an important parameter, but in some of the other locations, it's not. So this here, I'm showing just the list of the input parameters that we have selected. Then here showing you some of the examples of the type of failures that it can detect. So it can detect shallow rotational failures or deep-seated failures, like the one here showing on the Red Valley on the phase 3 location. Then after we finalize the selection of the input parameters, we go and do, as I mentioned, field verification. Because the model's capability of identifying slope failures anywhere, it's very important that we do actually verify it in the field. And we did have locations and phases where we have to adjust, remove parameters, or adjust the weights based on incorrect predictions. So for example, here on the left side, we have original model was indicating all this red region, all of this region to be a red, meaning a high risk for failure. But then after going into the field, we adjusted it and show it was showing that it was less risk. So there was this field verification is very important. The selection of the sites were made carefully by the consultant with input from geologists and geotechnical engineers with extensive experience with failures all around the states. So we selected sites with different geomorphology, different geology, different hydrology, and sites that have failed before, like the one that I showed you early on Trunk Highway 210, on Jay Cook Park, and sites that did not fail. As an example, here you can see in phase 3 location where you can see from the photograph that you see landforms, but you don't see anything major. But once you actually look at elevations, you can see shapes of the land. You can see potential locations where it could be, risky in terms of slope failures all along your highway. And then the model shows you, red areas of high risk, yellow that are not that risky, or green regions that are okay in terms of slope vulnerability. So after the model is developed, then we come up with what is called a risk matrix. So the model gives you what is here in the rows. So the likelihood or the probability of failure. So from the model, we get these numbers. So if we have a slope that is unlikely to fail, or if it's possible to fail, or if it's likely to fail. And then the managers and risk asset team comes up with the consequences and gives a rating for the consequences. And then these two numbers combined, the likelihood of failure times the consequence, will give you what is called risk. And that risk, we use it to develop some management areas. So of course, red, this score of 20, we need to do something about it. So we need to go to the site and do a more geotechnical based analysis when we have situations where they're red. Green one, we don't have to take any action. We can move ahead with the project, and we can move forward with any project that we are developing there. So here I'm gonna, so it's an example of how this preliminary management areas look like in the map that eventually engineers are using in Minnesota for their projects. So these preliminary management areas are basically delineated areas in GIS maps that have very similar risk ranking. So we have a recent verification of the model, was pretty cool. We have a recent failure in Trunk Highway 22 in Mankato, near Mankato, Minnesota. We have these two failures in these two locations. These maps, the maps for this zone were developed in 2017. So they were developed 3 years ago. And they were showing those two areas, they were showing red region, meaning that we needed to go and visit the site and take an action because it was high risk. So that was it felt pretty good about these encouraging validation results of this high level, network level model.
Raul, you have half a minute left.
So as closing remarks, these GIS models, yeah, thank you. It helps identify, map, and categorize slope failures. It assists in risk evaluation during project development. Is data-driven, it's time efficient, so it covers large geographic areas, and can be used for what we call the geotechnical asset management. It's a new mandate from Federal Highway. There are several resources. There are other people doing the similar work, like NASA has developed a landslide viewer. I highly recommend you guys watch this, check this out. It's a pretty cool tool. And if you're interested in more details, the reports from each phase are listed here. So with that, I'm open to any questions if there is any.